So welcome to lecture 2 of dual nature of radiation and matter. In the lecture 1 we have come across this equation where we said that the maximum value of kinetic energy of the emitted photoelectron is equal to the incident energy minus work function, and for the incident energy we have used the value of h mu, which is equal to h into frequency or is equal to hc by lambda based on the Planck's hypothesis. So these are the things which we have come across. So now in this second lecture we will be beginning to understand the experimental setup of understanding or performing the photoelectric effect. So I'm drawing a rough diagram of the experimental setup or the arrangement that was necessary for understanding the photoelectric effect. So the first thing that I am drawing is a photosensitive plate. So there is a photosensitive plate which we have. It is also called as the emitter plate, from which the electrons will be emitted. And we are taking out a terminal from this which will be eventually connected to a battery. It is placed inside an evacuated glass chamber. It is placed inside an evacuated glass chamber, and on the other side of the chamber is the another plate which we call as the receiver. We can also use the term of cathode and anode, but we are not using that term because we will be changing their potential during the course of experiment. So this is how the incident light is striking the photosensitive plate, and because of the photons striking the photosensitive plate, the electrons are emitted. Now these emitted electrons will start moving towards the collector plate in this way. So now over here in the first arrangement which we are doing, I am connecting it in such a way that I say that the this plate is connected to the negative terminal and this plate is connected to the positive terminal, and over here in between we can use a rheostat to maintain the required value of potential difference. So it is something like this. So now if I understand this arrangement, so this arrangement is somewhat like this, that an incident energy which we have explained in terms of h mu or hc by lambda is incident on this metal plate or the photosensitive plate, which is having a work function of phi. Now when the incident energy is greater than the work function of the photosensitive plate, the electrons are emitted with a certain value of kinetic energy, and the maximum value of kinetic energy is calculated as the incident energy minus work function phi. So this is the maximum value of the kinetic energy of the emitted photoelectrons. Now these photoelectrons which are emitted from this plate, which we are marking over here with a negative terminal, and on the other side is a positive terminal. So as a result of this potential gradient, the electron will start moving towards the positive plate with an accelerated value of voltage, that is with an increased value of kinetic energy, and will strike the other plate which is positive terminal, and due to this flow of electrons a current will be recorded which we call as saturation current, or we can also call it as photocurrent. That is the current which is generating because of the photoelectrons that are emitted from the emitter plate. So this is one portion of the experiment which we have understood. Now if I redraw this arrangement in such a way that we change the terminal of the battery. So I am drawing this arrangement little quickly this time. So this is the evacuated glass chamber that we have. This is the plate on which the light was striking, and this time I am connected this with the positive terminal, or I can say this one is the positive terminal and this one is the negative terminal. So we have done something like this time. So now this time what will happen is the light energy or the photons which is striking the metal target will definitely get some electron emitted if the value of incident energy is more than the work function of the metal plate. But now what will happen, uh, the electron which are ejected with very low kinetic energy are attracted back to the positive terminal. So this is the positive terminal, and as a result of which the electron which is emitted with a less value of kinetic energy is again attracted back to the positive terminal, and it failed to reach the other end, which is maintained at a negative terminal. So those electrons which have very high kinetic energy will surely rush to reach this negative plate and will constitute a value of photocurrent. And this is the reason that if we look at the graphical variation of voltage and current for the photoelectric effect setup, we obtain a graph like this. So let us understand this. For a particular intensity of light, the graph is attained somewhat like this, where on this end we have maintained the negative potential, that is reverse potential is maintained, and after this the graph is somewhat like this. The graph is somewhat like this, and the value of current over here is regarded as saturation current. This is regarded as saturation current. And the value of voltage, this is IV graph. The value of voltage at which no photoelectrons will reach the other plate is regarded as stopping potential. Is regarded as stopping potential. That is, if I continuously start increasing this value of voltage, that is, if I start increasing the positive polarity and this negative polarity is continuously increasing, then the electron which is having the maximum value of kinetic energy will also be stopped at a certain value of applied voltage in the reverse fashion, and this voltage is regarded as the stopping potential. That the maximum, the kinetic energy, the electron with the maximum kinetic energy is also stopped. That is regarded as cutoff potential or the stopping potential for the photoelectric effect setup. So let us understand this in a illustration like this. So I am explaining it with a setup like this. Let us consider something like this, that there is a metal plate having a work function, let us say 2 electron volt, and some incident light is striking this metal surface such that the incident energy is equal to 3 electron volt. So in this case, if I calculate the maximum value of kinetic energy of the emitted photoelectron, so the maximum value of the energy is equal to 3 minus work function, which is 2. So we attain a value of 1 electron volt. So the maximum value of the emitted photoelectron is going to be 1 electron volt. So now this story ends the moment the electrons are emitted from this metal surface and the maximum value is regarded as 1 electron volt. So if I say something like this, that it is maintained inside an evacuated tube. Now if I say that this is maintained inside an evacuated tube such that I say it is maintained at a negative terminal and this one is maintained at a positive terminal, and we say that there is a potential difference of 5 volt that is existing between them. So now what will happen, due to this applied voltage which is 5 volt, the electron which is emitted over here with a value of 1 electron volt will be accelerated because of this 5 volt potential difference and will reach this plate with a value of 6 electron volt. So the kinetic energy, I say, due to the collector plate being maintained at a positive potential, being maintained at a positive potential, the electrons accelerate, the electrons accelerate and strike the plate with greater kinetic energy. So this is what is happening over here. The electrons are emitted with this kinetic energy value, that is 1 electron volt, but because of the voltage that is applied across the evacuated tube, the electrons accelerate and strikes the plate on the other side with 6 electron volt. So if I consider this same arrangement, if I consider this same arrangement in this way, that this is the same metal plate that we have having a work function that was phi is equal to 2 electron volt, and the incident light that was striking this metal surface is having an energy equal to 3 electron volt, which is regarded as the incident light, and it is again placed in this evacuated chamber like this, where the other end is maintained at a certain voltage. So this time suppose I am keeping this at a negative voltage and this one as a higher voltage having a value equal to 0.5 volt. So if I do the same calculation over here, I will say that the maximum value of the emitted photoelectron is going to be incident energy minus work function phi. So the value of incident energy is 3 electron volt minus work function, which is 2 electron volt. So we get a value of 1 electron volt. So the maximum value of the emitted photoelectron this time is equal to 1 electron volt, but this time it is maintained at a negative potential and this one at a positive potential, and the value is equal to 0.5 volt. So as it will accelerate on the other side, it will be accelerated with a value of 0.5 electron volt, and the kinetic energy of the electron reaching the other plate is equal to 1 electron volt plus 0.5 electron volt. So we get a value of 1.5 electron volt. Now I am repeating this same experiment by reversing the terminal of this battery, and I am clearing it out. I am reversing the terminal of the battery and I am reversing the data which we have attained. This value remains unchanged. The maximum value of the kinetic energy of photoelectron remains unchanged. So this time I am saying that we are maintaining this plate at a positive terminal and this one at a negative terminal, and the value is equal to 0.5 volt. So now what is going to happen this time? Now this time the plate, the electrons which are ejected with low kinetic energy. When I say low kinetic energy, I mean to say that when we say that this is the maximum value, so there is a possibility that the particular electron is emitted with a kinetic energy of 0.5 electron volt. So that will fail to reach the other plate this time, because this time it is not accelerating but retarding the emitted photoelectrons. So this time the potential difference that is applied is the reverse potential difference, and the potential difference is retarding the electrons from reaching the other plate, from reaching the other side, and hence I say that the kinetic energy of the electrons reaching the collector plate, so this time it can be written as 1 electron volt minus 0.5 electron volt. So the value turn out to be 0.5 electron volt. So if the potential difference will be applied in such a way that the electrons accelerate, or as I say that this is maintained at a positive terminal and the other one is maintained at a negative terminal, then what will happen? The electron will accelerate. But if we say that the emitter plate is maintained at a positive terminal and this is maintained at a negative terminal, the electron will decelerate, and the value this time is obtained as zero point 0.5 electron volt. In this same experiment setup, if I say that the potential difference applied over here, the potential difference that is applied over here is equal to 1 electron volt, is equal to 1 volt, sorry. The potential difference of 1 volt is applied in the same setup where the incident energy is 3 electron volt and the work function is 2 electron volt. So this time what will happen? Due to this voltage, it will retard all the electrons from reaching the other plate. Because the kinetic energy of the emitted photoelectron, the maximum value is 1 electron volt, and a 1 volt potential difference in the reverse fashion will retard all the electrons from reaching the other plate, and this time it is regarded as stopping potential. So the minimum value of potential difference that is to be applied between the emitter plate and the collector plate so that no electron reaches the other side or the receiver plate is regarded as cutoff potential or stopping potential, and that is what is done in this particular graph. That is what is done over here in this particular graph. If the value of potential difference is more, that is in the positive side, then all the emitted electrons, will successfully reach the receiver plate. Whereas when we start applying the value of potential difference in the reverse fashion, then the kinetic energy of the emitted electrons will start decreasing. So the kinetic energy of the maximum photoelectron will be stopped at the value of stopping potential. And since all the values of emitted photoelectrons, that is when we say that kinetic energy maximum is 1 electron volt, so I mean to say that the emitted photoelectrons can have all the possible values of kinetic energy ranging from 0 electron volt to 1 electron volt, and that is the reason that we have this continuous line, because some electrons over here are stopped at zero point 0.5 voltage potential difference that is applied, and which brings it to a drop in the saturation current, and eventually in the particular example which we took, at 1 volt of stopping potential, all the photoelectrons, that is the maximum uh, uh, the electron which is emitted with the maximum kinetic energy is also stopped, and that is why we mark this as stopping potential. So this is how we explain this particular graphical representation and the concept of stopping potential. If we look at the other graphs, so as I have already explained in the previous lecture or the lecture 1, that if I look at the graphical variation of photocurrent and intensity, so we will be seeing different graphs. So this graph we have already understood, but we have not drawn this graph. So if we consider this graph, so I say that this graph is going to be a straight line graph like this. And why I am saying this is because as we increase the intensity, the number of photons striking the metal plate increases, which increases the photoelectrons that is emitted from the emitter plate, and this one is marked as photoelectric current. So as the intensity increases, the photoelectric current also increases. The next graph that we draw is based on the variation of photocurrent with intensity and potential. We have already seen for one intensity, We will see this graph for different intensities. So I write it as photocurrent versus voltage at different intensity. So on varying the intensity, the incident energy of per photon is not changing. It is only increasing the number of photons that is striking the metal plate. And hence if I consider something like this, so over here I am marking this part as the value of photocurrent I, and this one is the value of voltage. So for a light of less intensity, the saturation current will be low. The saturation current will be low, and this is marked as stopping potential minus V naught. If we increase the intensity, then the saturation current will also increase, but stopping potential remains the same because the maximum value of kinetic energy of the emitted photoelectrons remains unchanged. So if I mark this as the value of saturation current I3, I2 and I1, and the corresponding value of intensity as capital I1, I2 and I3, then I say that I3 is greater than I2 greater than I1. So on increasing the intensity, there is an increase in the saturation current, but the stopping potential remains the same. The stopping potential remains the same. And this is the graphical variation of photocurrent with the collector plate potential for different intensity of incident radiation. The next graph which we are looking at is the effect of frequency of incident light or incident radiation on stopping potential, and we are considering that intensity is same on stopping potential. So I have already taught you in the previous lecture that if we increase the frequency, the incident energy increases, and so is the maximum value of the emitted photoelectron, which also increases. And if the maximum value of kinetic energy of the emitted photoelectron increases, then the value of stopping potential must also increase in magnitude. Value of stopping potential must also increase in magnitude. So if we consider this particular graph, so if we consider this particular graph, so if the intensity is kept same, the value of saturation current is going to remain the same. When the frequency of the incident light is less, so the value of stopping potential will be less. The value will rise, and then it will attain a certain value of saturation current. On increasing the frequency of the incident light, the value of stopping potential will also rise in magnitude, but the value of saturation current will be same if the intensity is same. And then this one is another graph which we attain. So these are the value corresponding to frequency 1, 2 and 3 respectively, and we can clearly see that this is V1, stopping potential for 1, stopping potential for 2 and stopping potential for 3. So I say that the frequency of the third light is greater than the frequency for second light, greater than the frequency for first light. The intensity is same, and this is marked as saturation current. This is photoelectric current or saturation current with the voltage, with the value of applied voltage. So this is how the graphical variation of all the parameters that we have learnt is chalked out or done in this particular graphical way. We are left with one more graph which is based on the equation of photoelectric effect. So the equation of photoelectric effect which we learned, that was based on the maximum value of emitted photoelectron kinetic energy is equal to incident light minus work function phi. So if I write this value in terms of EV, that is electron volt, and if I write this as h mu minus phi, then we can say that the value of stopping potential, or the value of potential, can be written as h by e mu minus phi by e. So if we look at this particular equation, it is of the form y is equal to mx minus c. It is of the form y is equal to mx minus c, and hence I can say that if we are plotting a graph, if we are plotting a graph for any metal, then the slope of the graph between stopping potential or potential V and frequency. So on Y we are marking potential, on X we are marking frequency. The slope remains the same, h by e is constant. So for any metal, the slope of this graph remains the same. The slope of this graph remains the same, and the slope is equal to h by e. So if I call for this as a metal 1 or metal A, and this one as a metal B, so we obtain a graph like this, such that the slope of this graph theta A and theta B, so the slope of this graph, slope is written as tan theta A, which is equal to tan theta B, and this is equal to h by e, and the value of y intercept is equal to phi by e. So this is equal to phi for A divided by e, and this one is regarded as phi for B divided by e, and I can say that phi B is greater than phi A. That is, work function of B is greater than work function of A. Work function of B is greater than work function of A. So greater value of work function implies what? Greater value of work function implies bad electron emitter. So B is not a better electron emitter, A is a better electron emitter. So A is a good electron emitter. Good electron emitter. And as far as B is concerned, it is a bad electron emitter. So in this segment we have come across different graphical variations, and have learnt about their implications or the effects on the equation of Einstein, that is kinetic energy maximum is equal to EI minus phi. In the next segment we will be beginning with the numericals based on this photoelectric effect.